This is our second video on the topic vector fields. In last video, we were defined the set Rpn plus 1 and proved that it is an inner product space under the dot product defined on Rpn plus 1. Next, what is a vector field? When we define the vector fields, a vector field on a subset U of Rn plus 1 is a function which assigns to each point P belongs to U a vector at that point. That is x of P equal to Px of P, where x of P belongs to Rn plus 1 for some function x from U to Rn plus 1 is called a vector field, and the function x is the associated function of the vector field x. For example, consider the vector field on R2 defined by x of P equal to Px of P, where x of P equal to ordered pair 0, 1. This vector field maps each point in R2 to the vector 0, 1 at that point. And we can visualize the vector field as in the figure. Next, we are going to define a smooth vector field. Before that, when we say that a function, a real valued function f is smooth, a real valued function, that is f from an open set U to R, is smooth if all its partial derivatives of all orders exist and are continuous. When we consider the function f of t equal to sin t for t belongs to open interval 0 pi, sin t is a differentiable function on the open interval 0 pi and derivative of all orders exist on the open interval 0 pi. Hence, it is a smooth function on the 0 pi, open interval 0 pi. Similarly, we can say that f of t equal to cos t is also a smooth function on the open interval 0 pi. And a function f from the open set U to Rk in the form f of p equal to f1 of p, f2 of p, etc. fn plus 1 of p is smooth if each component function f5 from U to R is smooth. For example, consider the function f of t equal to cos t sin t for each t belongs to open interval 0 pi. Since cos t and sin t are smooth function on open interval 0 pi, we can say that the function f of t equal to cos t sin t is a smooth function on the open interval 0 pi to the set R2. Now we can define smooth vector field. A vector field x on an open set U in Rn plus 1 is smooth if the associated function x from U to Rn plus 1 is smooth. For example, consider the interior of the rectangle 0 pi cross 0 pi. Now define a vector field on the interior of the rectangle by the function f of xy equal to ordered pair cos x sin y. We know that the function cos x and sin y are smooth functions on the open interval 0 pi. Hence, the function f is a smooth function on on the interior of the rectangle 0 pi cross 0 pi, and hence we can say that the vector field is a smooth vector field. We know that any constant function is a smooth function. So we can say that the vector field that we defined at first is also a smooth vector field. Gradient vector field. Let U be open in Rn plus 1 and f from U to R be the smooth function on U. Then the vector field defined by gradient f of p equal to p dou f by dou x1, dou f by dou x2 of p, etc. dou f by dou xn plus 1 of p is called gradient of f. Consider the function f of x1, x2 equal to x1 plus x2 on R2, which is a smooth function. Consider the partial derivatives of this function. That is dou f by dou x1 of x1, x2 equal to 1 and dou f by dou x2 of x1, x2 equal to 1. Then gradient of f at x1, x2 equal to x1, x2 dou f by dou x1 of x1, x2 dou f by dou x2 of x1, x2, and which is equal to x1, x2, 1, 1. That is, the gradient vector field maps each point to the vector 1, 1 at that point. Next, consider the function f of x1, x2 equal to x1 square plus x2 square on R2. Then the partial derivatives of these functions are dou f by dou x1 equal to 2x1 and dou f by dou x2 equal to 2x2, and gradient of f at the point x1, x2 equal to x1, x2 dou f by dou x1 of x1, x2 dou f by dou x2 of x1, x2. That is equal to x1, x2, 2x1, 2x2. Parameterized curve. A parameterized curve in Rn plus 1 is a smooth function alpha from I to Rn plus 1, where I is some open interval in R. That is, any smooth function from an open interval I to Rn plus 1 is a parameterized curve. Consider the function f of t equal to sin t cos t for t belongs to open interval 0 pi, which is a smooth function on the open interval I. Hence, it is a parameterized curve in R2. Also consider the function f of t equal to ordered pair t square on any open interval I. We know that this function is a smooth function on any open interval in R. Hence, it is a parameterized curve in R2. Velocity vector of a parameterized curve. The velocity vector at time t of the parameterized curve alpha from I to Rn plus 1 is the vector at alpha of t defined by alpha dot of t equal to alpha of t dx1 by dt of t, dx2 by dt of t, etc. dxn plus 1 by dt of t. Now you know about the smooth vector field, parameterized curve, and the velocity vector of a parameterized curve. Next, we are going to define the integral curve of a smooth vector field. For that, consider a vector field x in R2 and draw a parameterized curve, that is a smooth curve in R2, so that the velocity vector at each point alpha of t is equal to x of alpha of t. Then this curve, this parameterized curve is known as the integral curve of x. In general, we can define an integral curve of a vector field. A parameterized curve alpha from I to Rn plus 1 is said to be an integral curve of a vector field x on the open set U in Rn plus 1 if alpha of t belongs to U and alpha dot of t is equal to x of alpha of t for all t belongs to I.